Where's everybody? All right, so it is the appointed hour. It's time for me to talk. So, how was the hurricane, or lack thereof? It's nice to get that time off, I guess. Nothing happened in Wailuku. Nothing. I mean, it was like a little bit of rain, a little bit of wind, but it was a non-event. I mean, I'm happy it's a non-event, but you look at me kind of strangely. Did something happen at your place? Or? No?
No.
Yeah. No? Nothing? Okay.
Yeah, nothing.
It looks like Lahaina got hit the worst with the fire.
Honestly, I flew get choke rain.
Yeah.
Like 18 inches.
Where?
Hana.
Hana? Oh,
That
jeez.
east side.
And Hilo got like, what, 40 inches? It's like Venice there. Oh.
Almost 4 foot water or something. Crazy.
Yeah. It's crazy. All right, well, we're here. We're a little behind, but that's okay. We can make things up as we go along. And so today we're going to jump topics. The first couple of classes we jump topics quite a bit. And that's just because it's the beginning of the intro. And so this is a chemistry class. Probably a good place to start is to define what chemistry not 30, I'm sorry, 15 Celsius. So it's about a 30 or so Celsius greenhouse effect. And most of it comes from water. And the climate models, carbon dioxide is just not a very strong greenhouse gas. The idea is that carbon dioxide causes more water vapor to evaporate from the oceans, which causes global warming. That's by a process called climate forcing. And Fukushima, most civilian nuclear power plants, well actually all of them, use water in them. Water is used in a lot of places. It's found in cancer cells. It's found in all cells. We don't have any cells that don't have water in them. Used in animal research. Gotta feed water to the bunny rabbits. Huge investment in warfare. Heard the Navy before, right? So, and this is all water. Everything is true, but it can be taken out of context. So, one of the ways to avoid being duped by stuff like this is to know everything beyond which, to not be duped by things out of context. So let me talk about some other sciences, and these are kind of considered the big three: biology, physics, and chemistry. So biology is the study of life, so studying life, studying biology. Physics is the study of the physical world, and I don't like the fact they have physics and physical world in the definition. To me, physics is how long the vector is and where it points. So If you look at my center of gravity, it's being pulled towards the center of the Earth. I have a weight of 260 pounds. So 260 pounds, vector is going straight towards the center of the Earth. The floor has an equal opposite normal force, which is then perpendicular to the floor, that is equal to about 60 pounds. And it depends on how much I lean one way or the other, I guess. That will keep me from falling over. So that's kind of stuff with physics. Chemistry is the study of matter. So this kind of encompasses quite a lot of things that we care about: life, the physical world, and matter. Chemistry is actually kind of a subset of physics, if you think of it that way. And you could also argue biology is a subset of chemistry, just a different kind. There's other sciences, at least what we consider to be the hard sciences, things like geology. So that's the study of the Earth, and or geophysics, the physical part of study of the Earth. Oceanography, study of the oceans. Marine biology, although it has biology in it, study of marine life. But in general, these are the big three. And the other thing you notice about biology, physics, and chemistry, they have the most majors, they have the most jobs in them. There isn't really any outreach for these. The outreach that you see is more towards the ones that don't have any direct use. So things like astronomy or marine biology. There's not a whole lot of use for marine biology. So when we have an ocean center here geared towards outreach for that, there are lots of centers for outreach for astronomy because it's not as useful. So say I'm going to spend $1 billion studying cancer research drugs. So why do I want to spend $1 billion studying drugs for cancer? Of course, because we want cancer drugs. I want $1 billion to build a rocket. Why? Because I want to go to Mars. Why do you want to go to Mars? What does that have to do with me? Why do I care sitting on the beach watching the sunset in my chair that you're going to Mars? So cancer drugs, I like a cancer. I want those drugs. But the rocket to Mars, I don't know. Or I want a telescope up in space. Why do you want a telescope in space? It's interesting, but it's not directly useful. So there is some outreach in chemistry. I've done it myself, but it's mostly educational oriented. And it's kind of just like, a booth at the mall or something like that, or here on campus. So, but let's talk a little bit more about chemistry. There's a couple main branches of chemistry. The old main branches, well, the biggest branch of chemistry is what's referred to as synthetic chemistry. It's the chemistry where you make stuff. So like Heisenberg in Breaking Bad, he's a synthetic chemist. He makes things. Physical chemist, that's the physical side of chemistry. That's me. I'm a physical chemist. And they're much more synthetic than physical. And now a new branch that's been forming is biological. So the lines between the majors are starting to skew. So if you're a biochemist, if you're a molecular cell biologist, it's getting closer to each other as far as what you're studying. Okay, then science. What's the definition of science? If you hear saying someone, oh, I'm doing this, I got this down to a science, it means a systematic approach to solving problems. So if you are going at ways in a systematic approach, that's what a science is. And specifically what science uses is something called the scientific method. So this method that science uses is the scientific method, very original in these names. So let's talk a little about the scientific method. And the scientific method starts with observations. So something you observe. And observations can be either quantitative or qualitative. So quantitative, quantity, are number-based. Qualitative means idea-based. So what do I mean by that? The wall in the back of the classroom is blue. That's an idea. The photon of light coming from the wall is 550 nanometers, thereabouts. Quantitative, I put a number to it, 550 nanometers. This is a small class size. I have 20 students registered in the class. So when you add an idea or a number to an observation, it becomes quantitative. And if you have enough observations, you can get what's called a scientific law. So with enough observations, you can go right to a scientific law. So a simple law is the law of gravity. So law of gravity is what goes up must come down. What goes up must come down. I can do this all semester long, and we can verify the law of gravity, right? Kind of a boring class. Can you break the law of gravity? Yes, you can. Voyager probes, we sent them up. They're leaving the solar system. So what comes up does not have to come back down. You can break scientific laws. So scientific laws can be broken. And next I'll talk about theory, how theories work. So then the other part of the scientific method is to form a theory. And how does one form a theory? Well, with enough observations, one may form a hypothesis, which is an educated guess based off of the information that it has. It doesn't necessarily have to be an observation. You can also have a hypothesis from theory. So, but theory being from previous data, which actually comes from observations. Then an experiment is done to test a hypothesis. Then the hypothesis is either revised or it is confirmed. And after the hypothesis is confirmed, it becomes a theory. So as a simple illustration, say I go to start my car and my car doesn't start. So I hypothesize that, you know what, maybe my battery's dead. So then I go, well, you know, if my battery's dead, then my lights won't turn on. So flip the light switch, oh, the lights turn on. It's not my battery. I say, maybe I'm out of gasoline. So what do? I go and I get some gasoline, I put it in the car, then I turn it on, and it starts. Like, oh, I've just, by experiment, I've confirmed my hypothesis that my car didn't start because it's out of fuel, and now that has become a theory. So, I mean, of course, this is a very simplified version of the scientific method, but there's some very powerful theories out there. Theories like atomic theory, that's a big theory, and also theories can be wrong, and they can be partly wrong but mostly right. So atomic theory, we'll talk about a little bit next class, but when atomic theory started off with Dalton's atomic theory, he thought that atoms were like spheres, or like well, they are kind of spheres, but they were hard spheres, like the ball pit in McDonald's. He thought that atoms were like really hard spheres, like the ball pit in McDonald's, and they were all the same. Then they found out that's wrong because you can rip electrons off of it. So they thought then that atoms were like blueberry muffins. It's called the plum pudding model, but we don't eat plum pudding here in the United States. But the blueberry muffin is like, you know, mostly muffin with blueberries in there. The atom then became a very big sphere of positive charge with electrons floating around inside, like blueberries in a blueberry muffin, or plums and plum pudding for people from England. So then there's other iterations to talk about. But I mean, now we have the quantum mechanical model for the atom. That could also be wrong because maybe string theory will be confirmed. So, okay. So, and theories don't necessarily describe everything. The germ theory for illness, that does not describe every single illness that we have. So, for instance, I mean, before we thought, we didn't know that pathogens caused illnesses. And mind you, pathogens cause most illnesses. But we thought things like malaria. Malaria literally means bad air. We didn't realize it came from mosquitoes. We thought, oh, if you breathe in bad air, you're going to get malaria. You know, when it's actually mosquitoes biting you and passing on a vector disease. While other diseases, cancer, maybe some cancers are caused by pathogens. There's a lot of causes for cancer. One might be pathogens, but cancer is not necessarily pathogen-based. It's mostly not. Radiation sickness, caused by radiation, no pathogens. Mental illnesses, if you want to consider them the same as the disease. dermatitis, which inflames skin. That's a disease. It can be caused by poison ivy. It can be caused by jellyfish stings. It can be caused by sticking your hand in bleach for too long. So, I mean, those are all diseases that are not necessarily covered by germ theory. But germ theory is still a very powerful theory. Just because something isn't described by it doesn't mean, oh, nope, well, my radiation sickness didn't come from a disease. Throw out germ theory, that kind of thing. So, but the whole idea here is it's an iterative process, meaning we go over and over again. And so that way we can build up upon past knowledge and generate new knowledge. So this is what is in there. Okay, oh, and I have here some of these symbols. If you see a symbol you don't understand, you're welcome to, this is an open discussion. We can talk in class kind of thing. Hand up is appreciated, of course, but I mean, like, I don't necessarily have to talk in autopilot the whole time. This capital sigma here, this means sum. So this symbol here, and one of the things we're taking these courses is that you start to see what the symbols mean. The capital sigma means sum, summary of sum of observations. Okay, and this is what I talked about here: a hypothesis, educated guess, experiment, do the test a hypothesis, a theory is a proven fact. And the thing, theories can be and often are wrong. So, and they can be wrong in certain contexts and not in others, like germ theory. Laws can be broken. And another thing with science, that science is tentative. So meaning, it's we're learning new things every day. And contemporary science, so contemporary science like right now, is experimentally based. So we do not base our science and understanding off of models or simulations. So, and I mean, we're getting better with our models. I mean, the hurricane coming through, that was a pretty scary model, right? But I mean, the models changed, and of course they got better as the closer we got. What we really care about is what actually happens. So we don't care that the model originally showed a Category 2 storm plowing through Maui. We care that it missed us. So, and this is in direct contrast to the way things were like around the year 1850 and before, because back then we were also sometimes called the Age of Enlightenment, and it's by the fact that we consider what is real, what we can prove experimentally. To give you an example, back in ancient Greece, especially with Plato, so like with the Platonic ideas. So Plato literally believed that there was a veil. There was heaven, then there was a veil, and there was earth and like stars. You could see where holes in the veil. And like if you look at something like a chemistry textbook, there was this perfect chemistry textbook in heaven, and everything else you contrast that to. And we sometimes, so inaccurately in colloquial English right now, we have something we call Platonic love. So we use it inaccurately to the ancient Greek model. So Plato thought that Platonic love could only happen between two males. So perfect love was between two men. And it was a Stoic kind of love, meaning there was no attachment. And so, like if you've ever read the Apology where Socrates killed himself, executed by Hemlock, right? He was like, oh, I'm going to die. All right, drink it. All right. And, I give up on life. So that's the Stoicism. So, of course, colloquially now, or to say contemporary version of Platonic love can include female-female and male-female and whatever other combinations thereof. So it's, but again, it's different ancient Greece. It was the idea-based, the perfect model-based. Whereas now it's about what we can prove. And science has taken a huge jump since then, since the 1850 thereabout. Another thing that's used very extensively and poorly is correlation being the same thing as causality. This is very bad to use. If someone says this correlates this, so this indicates that what that person's saying is I'm not a scientist and this is not a scientific discussion. Sometimes correlation can be used, but it's very difficult. I mean, like you're like, well, I can correlate my headache with being hit in the face with a bat. So therefore, but correlation does not mean causality. So I don't know what's going on here. Let me give you a different example. I mean, that's obviously not the proper use of it. You're getting a blunt force trauma to the head. But the back when polio outbreaks were happening, they were able to correlate ice cream sales with polio outbreaks. So what they would what they started telling parents was, don't buy your kids ice cream because ice cream could cause polio. Okay, so what's going on though? Polio is a pathogen. Okay, a pathogen caused polio, and well, it's hot here all the time in Hawaii. But if you go to somewhere like Wisconsin that has a winter time, in February, you're not going to take your kids out to eat ice cream. So although in June, July, when it's hot, there's a swimming pool, like, you guys want some ice cream? It's a hot day. What do? They hang out with their friends. They're all, they wrestle around in the mud, and they go, oh, ice cream, and they touch their hands in the ice cream. They eat the cones, that kind of thing. They're exchanging pathogens just by being in proximity and by their activities. So the fact that the more interacting with people happens in the summertime is the reason why the pathogen was more virulent in the summer versus the winter. And the fact that that it correlate was only because it had a common third factor. So that's called a common third factor, where they don't necessarily mean a causality, but they have something in common. But then again, you get things that correlate that have nothing to do with each other. So, I mean, what if I correlated, like I said, all right, how many peanut butter sandwiches have you eaten the past year, and how many flat tires did you have? And what if I could find a correlation between the two? Does that mean anything? Or what if I said, how many blockbuster movies of actors wearing red shirts happened versus number of chemistry sections offered at Maui College? Do those have, what if I had a perfect correlation or near perfect correlation? Would that mean anything? No, of course not. You can get correlations that are absolutely nonsense. And the other part of science is very powerful. So it is one of the major backbones of our economy. So one of the things they are telling me is, like, we need more STEM majors. So STEM, science, technology, engineering, mathematics. So without STEM majors, our economy is going to stall. And in fact, we import many people with STEM degrees. So America does not generate very many STEM majors. So it's powerful because it's useful. And also, science itself has some power to it. We can use science to put people in jail, right? We can use forensic evidence as proof in trial. And the science can put people in jail. And bad science can severely injure people. And here's an example of bad science. It's a science, I even hate using the word science, is science called eugenics. So this happened right after the science of genetics came out. Eugenics came out, and eugenics is the belief that there are different races of humans, and then these different races of humans, if they intermix, then the human race will become extinct. So even today, we still have that. We use that colloquially. Like, you see on some forums, they ask you what your race is, right? And you're like, the proper answer is human. There's only one race, because if you look at well, by natural species, if two members of the same species breed, and if the offspring is fertile, then it's considered to be the same natural species. Although there is some fuzziness within that. But if you look at, like I did the 23andMe, apparently I got some Neanderthal blood in me, or DNA. So are we the same as Neanderthals? That's another thing. Like, well, there are different species in that regards. But as far as humans, no, there's not different races. So At best, we can say that we have subspecies. Like tigers have Sumatran, Bengal, Amur tigers, for instance. We humans might have 3 main subspecies, basically, well, Caucasoid, Mongoloid, Negroid. So white, black, Asian, basically. So, but humans, the model doesn't work as well as it does with tigers because humans intermix so much anyways. And so it's not a very good model. But the idea, but the other part with eugenics is that the Nordic, so the Nordic race, that was the genetic superior one. I'm Nordic, so I'm telling you it's complete and utter nonsense. So the blonde hair, blue eyes, that's the Nordic one. And there was some legal consequences for this. So has anyone ever heard of the Loving versus Virginia Supreme Court case? I've heard of that. Okay, someone in last class did. 1967. There was a series of laws called miscongenation laws. So it means different genuses, like the classification, the kingdom, family, class, order, family, genus, species. So different genus, the idea like, okay, we're different species. We can't have these different species of humans intermix. And it was really just whites could only marry whites. So people that were not white were, what was considered to be white could intermix. And the definition of white was someone who is of European descent that had less than it's either 1/8 or 1/16 Native American blood in them. That was white. So, but there was a case, the Lovings, they were as a white male, black female. They got married in Washington, D.C. Then they moved to Virginia, and D.C. did not have any miscongenation laws. Virginia did. They got arrested, and then they fought the case, went to the Supreme Court, and got thrown out. So now there's no, with American law, when that happens, when a law is considered unconstitutional, no one can pass any laws. They see even now you couldn't pass a law. Well, you could, but then you got arrested, you'd be thrown out. Also, United States. So what are the evil things that we do? We sterilized about 300,000 women that were mostly in Puerto Rico, that were considered to be genetically inferior. So, and this was a science. People held parties, and they had like showcases where they said, "This is the most perfect human specimen. Look at this specimen, so superior to everything." So, yeah, of course. I mean, some people are looking angry. I mean, it's complete and utter garbage, right? I'm married. My wife is Asian, so I would be going to jail back in the '60s. So, I don't know if Hawaii had any of those laws ever. So probably not. We're very melting pot here, right? So, but this was a belief, and it was backed by science. So, and that's bad science. What is bad science? Bad science uses correlation. Correlation's bad. Relies on models instead of experimental data. So the whole idea, the Age of Enlightenment, we use experimental data, and relies on consensus. So opinion, even collective opinions, are irrelevant in science. And like a discovery by nature breaks consensus. If consensus was important, we would never have any discoveries. So the consensus needs to be broken. Okay, so we're going to change topics. So we changed topics quite a bit in the beginning. Anybody have any questions before I move on? I'm sorry, we do change topics quite a bit. And chemistry, study of matter. So chemistry is study of matter and how it changes or doesn't change, if you will. And talk about the states of matter. So solids have a defined shape or definite shape and a definite volume. So my cell phone here has a rectangular prism shape, has a volume of about 50 milliliters. Okay, liquid, although this is not clear, there's water in here. It has an undefined shape, and it has a defined volume. So the shape of it right now, of the water in here, is a cylinder. okay, and the volume is about half a liter. Now it is a longer half cylinder shape because I've turned it on its side. But the volume hasn't changed. It's still half a liter. If I poured it into another container, it would take the shape of the container. If I poured it on the desktop, it would make a very oblate pancake-like shape. But it would be almost impossible. But the idea is if I was able to be very careful and get up all the water and put it into a container, I would have exactly the same volume. I mean, of course I wouldn't. There's scratches and whatnot on the table. And transferring it, I would some stuck on the material. But in essence, if I was careful enough, maybe I could transfer all the water into another container, and it would keep the same volume. So the volume doesn't change. And then we have a gas. Gas has neither a set shape nor a set volume. So if air is a gas, I can take my tire from my car and bring it up here like, what's the shape? What's the volume? Like, well, shape of the tire, volume of the tire. And if I were to slash a tire, it'd be like, well, what's the shape? What's the volume? Shape of the room, volume of the room. Gases just fill their containers. It's outright they are very not set in pattern-wise. And some people can argue that another state of matter is plasma. So what is plasma? Plasma is just a gas that is ionized, means it has one or more electrons ripped off. So in chemistry, we more or less consider gas and plasma to be the same, at least in terms of its interaction, meaning it's how it orders itself. Gas is similar to plasma by the fact that it would it just fills the space. And plasma also would follow the gas laws. So that's another argument for saying plasma is a gas. Some biochemists consider phase change to be the denaturation of proteins. So proteins have shapes, and what determines their function is the shape of the protein. So for instance, so I can move my hand, no problem. What would happen if I had third-degree burns all over my hand? Would I be able to move my hand? No, I couldn't. Because one of the things that changes the shape of proteins, denature them, is temperature. So increased temperature can do it. pH can also do it. So that's why, like lomi salmon, you put fruit juices in it. It cooks it. It denatures the protein. Makes it safer to eat. So in our stomach, also can denature things with the acid, with the hydrochloric acid in it. So, okay, so let me go back to talk about solids. Solids have two different forms, crystalline and amorphous. So crystalline means regular pattern, amorphous means irregular pattern. If you look at my MacBook here, it is made, the surface here is anodized aluminum. Okay, this surface right there, it is aluminum oxide, also known as sapphire. So sapphire means aluminum oxide. And whenever you, here on Earth at least, if you have aluminum, it is covered in a thin coat of sapphire. Anodized just means you make it thicker, and sometimes you put coloring agents in them. So like I have anodized cookware. They just put black, something that's black. I don't know what makes it look black. Well, it's probably Teflon on the top, and then anodized underneath that. Then I guess they sell some just plain old anodized in Costco. So it's kind of a gray color. I've had anodized. I used to work with lasers, and I had shields that were anodized. They were black. It's nice to have things black around lasers because black absorbs light really well. So this is anodized. It means it's coated in. It's got a little thicker than normal coat of sapphire, because sapphire is the second hardest natural mineral. So iron is weird. Iron rusts. When iron rusts, the oxide is very brittle. So whereas things like aluminum and titanium, when it oxidizes, the surface is really hard. So it'll react, but it doesn't corrode as easily because the surface is so hard. So that's why. So aluminum is great for that regards. But anyways, this is sapphire. You're looking at sapphire, and you can also go to a jewelry store and buy sapphires that are really expensive. What's the difference? One's crystalline, one's amorphous. This is a random pattern here, even though it was partially synthetically made. A sapphire, a true sapphire, like a pure sapphire, they're clear. So the blue sapphires, they come from impurities of iron and titanium. makes them look blue. And we also have red sapphires. If there's an impurity of chromium that makes a sapphire red, we also call those rubies. So rubies, well, since we call sapphire aluminum oxide, rubies are considered sapphires. So emeralds are something different. They're beryl. They're a different mineral. Diamonds are also different. They're just plain old carbon. But sapphire, like a lot of synthetic stones are sapphires. Like the most class rings, when you see those big gems on them, they're sapphires. You can make them in the lab really quickly and easily. So, but anyways, those are crystalline substances that has a regular pattern. Amorphous means irregular pattern. And even things that have pretty regular patterns can still be considered amorphous. So iron, if you look at any iron, the arrangement of the structure of iron is around 90% or so what's called the 110 surface. And at least on the surface it is. And that's just the surface that it's like a flat with all the atoms just flat. You can get certain structures of iron that are different. So the 111 surface. So if you have a surface with all the just plain old atoms on the surface, or you can have ones where you have kind of valleys where there's steps, like 3 atoms deep, and you have these valleys in them. That iron surface is extremely reactive, and because molecules can go in there and they can break apart inside of that. That's how we make ammonia that way. And so even though there is a little bit of the 111 and it's mostly 110, a little bit of 111 surface, and that's something called Miller indices, which we won't talk about at all in this class. It's just the arrangement of the atoms is different. And iron just sitting there is, even though it's mostly one way, it's still not completely crystalline. We can make crystalline iron. It's really hard to do. So it's a pain. It's very difficult to do. I've done it. It takes a long time. But most everything you see is amorphous. Okay, let me talk about how matter is organized. And I'm going to do it from the most general to the simplest, and then I'll build it back up. So we can do a double pass, if you will. And again, I'm sorry, I know I'm changing topics yet again. It's going to be the name of the game for the first couple of weeks. So all matter can be pure substances or mixtures. Most everything is a mixture. And let me start off with the most general mixture. The most general mixture is heterogeneous. So heterogeneous means non-uniform. And then there's homogeneous or homogeneous, either one is correct. This means uniform. Has anyone ever seen milk from a cow before? I have. So what is it like? It's chunky, right? So it's not uniform, right? And also, if you let it sit, it kind of spreads too, right? So it's chunky, meaning there's parts that are different than the other parts. It's not uniform. So if you buy milk in the store, it says pasteurized and no one ever buys milk. Homogenized. So homogenized milk. That means that the milk on the top is the same as the milk on the bottom. So you don't have any, if you had chunks in that, you're like, dude, chunks in my milk, I want a refund, right? So homogeneous, homogenized, so it means uniform. So we can take heterogeneous mixtures like milk and turn it into a uniform mixture. And we can even turn it into different uniform mixtures. We can turn it into skim 1-2% and whole milk too. We can even take different parts. We can make cream from it. So take the fat off the top. Homogenize that. Then we have cream. So then we can take uniform mixtures and we can break them into pure substances. So for milk, what's in milk? Well, there's water. There's calcium phosphate. There is milk fat. There's some fat in there. There's emulsifiers. There's proteins. There's whey, for instance, and casein. So there's different pure substances in them. And actually, for milk, they're all compounds. So compounds are a combination of elements, and then elements are the building blocks that we'll get to. So, okay. So elements, and the simplest unit of an element is an atom. So let's say, so the inside of your pencil is graphite. So I see some of you are writing with mechanical pencils, like one of those pencil leads. It's not lead, it's graphite, carbon. So what if I took one of those and I broke it in half? And I took that piece, broke it in half, and I kept on doing it. I will get to a point, if I break that in half, it will stop being carbon. That point is known as an atom. Okay, we can break carbon apart. So we can do that. You can take carbon, you can break it apart into lithium, or so 2 lithium atoms, or it can become 3 helium atoms. So we can do that with carbon. But once you do that, though, it's no longer carbon, it's a new element. And for the elements, we have them in the periodic table. There's one in the back of the classroom. I'll show you one here. This is a fun one. Here we go. Same one, Theodore Gray. The elements, so different things like copper. So an element's like copper. And the simplest unit of copper is an atom of copper. And okay, so let's go, now that we've talked about elements, let's go backwards. So we can take elements and we can mix other elements to form compounds. So with water, H2O, I can take the elements hydrogen, 2 elements of hydrogen, 1 element of oxygen, and I can make a new compound, water. And the compound water is nothing like its original elements. So hydrogen is a gas, it's explosive. Oxygen is a gas. Well, I don't want to say explosive. It's not a fuel. It's an oxidizer. It's highly reactive. Water is not very highly reactive, and it's a liquid at this temperature. And I can also do different combinations. I can take H2O2. That's hydrogen peroxide. If I drink water, it'll feel good. If I drink peroxide, it'll give me, at the very least, one really bad sore throat. It might kill me, right? So just with another oxygen, you change a new compound. Okay, but we can also then take elements and or compounds to form mixtures. So you can do it with elements. So 14 karat gold. It's a mixture of gold, silver, and copper. So that would be a homogeneous mixture. So 14 karat gold just has 3 elements all mixed together. I can take 2 elements, nickel and iron. I have a ring like this. It's a meteorite ring. So nickel and iron, you can get a little bit of nickel dissolved in mostly iron, a little bit of iron dissolved in mostly nickel, and it forms these kind of like these, like they look like little bands, like little shiny bands. It's a really pretty ring. That's a heterogeneous mixture. It's not uniform. You have 2 phases of nickel iron, and there are some meteorites that are nickel iron. So my wife's an astronomer, so that's one of the reasons why I have those rings. So okay, and we can also do it with pure substances, with compounds, right? So you can have here's, I guess, sugar water for tea. So you can have sugar and water, 2 different compounds, pure substance, it's uniform. And you can have water and sand. So sand, usually silicon dioxide, H2O, they don't mix. It's a heterogeneous, non-uniform mixture. We humans, we are heterogeneous mixtures. Right? So even most of the things we're made of, blood is a heterogeneous mixture. So most everything is a heterogeneous mixture. Okay. All right. And then let me talk about physical and chemical properties. A physical property, this is something you find without a substance change. So things like color, magnetism, boiling point. So phase changes, so solid, liquid, gas, those are considered a physical change. I can take frozen water, so solid water, ice out of my freezer. I can put it on my stovetop, turn on the heat. It can melt, turn into liquid water, that'll boil, and turn to water vapor. Then I can collect the water vapor, and I can condense that down to liquid water. I can throw it back on my freezer, and I'll get ice again. In that going from solid ice to liquid to gas, back down to liquid and solid, has it ever changed not being H2O? Is it the same compound? Yes. Or no, it has not changed. It has always been H2O. So changes of phase are not considered, or states, those are not considered to be chemical changes, a physical change only. or physical property. So you look at my shirt right now. I have a black shirt on, right? You can observe the fact it's black. This shirt is also flammable. That's a chemical property, because if you burn the shirt to verify it's flammable, it's no longer a cotton shirt, right? It's changed. So that's a chemical property. Chemical property dealing with composition changes, or kind of exchanging of atoms, or lack thereof, like gold. So we always thought gold was a magical substance. So, and we use chemical properties in unique ways. So we give rings based off of the metal's chemical properties. So, of course, the noble metals, the non-reactive metals, tend to be more expensive. So, and it's also not a rarity. So platinum is more expensive than gold, but platinum is more rare than gold. So, I'm sorry, gold is more rare than platinum. Sorry, other way around. Platinum is more expensive because it's more useful. So, but platinum is similar to gold. It's not reactive. The most expensive metal, if you want to go by expense and value, is weapons-grade plutonium. So are we going to start giving rings made of weapons-grade plutonium? No, we won't. It would be stupid for many reasons. Number one, plutonium is a toxic metal, it's reactive, and it's radioactive. So it's not a very good thing to have in your possession. So why do we give gold rings then? Well, let me look at it the other way. What if upon proposing to my girlfriend at the time, I said, "Darling, I love you. My love for you is as strong as iron. So I present you, as a symbol of my promise, this iron ring." Right? So, but why is that funny? It's because iron rusts. So iron rusts. Even the cheap rings, like silicon carbide rings. I mean, I don't know why you go to good jewelry stores and buy them. You can make it like, it's so cheap. I mean, like you can, if you look online, you can find one for like $5 because it's a cheap substance. But it's really hard. It's really hard. It's shiny and it keeps its shine for a long time. So we like things that are shiny that stay shiny for a long time, because we think they're magical. Gold we thought was magical because it doesn't rust, and it has some religious significance too. The Incans thought that it was sun sweat or God sweat, so that was the gold. And like I said, it doesn't tarnish. So the ring I proposed with was my grandmother's ring. So I mean, we can keep rings in families for a long, long time. It was also a diamond ring. We think diamonds are also magical. This is a long-going thing. So you ever heard diamonds referred to as ice, like in like rap songs and stuff? Like, why do we call diamonds ice? I mean, say plastic, polycarbonate. You know, like if you take chunks of polycarbonate, like stuff I store food in, it looks like ice too. You know, why don't I call that ice? It's because diamonds. If you have a diamond and you touch it, it feels cold. So diamonds have a really high thermal conductivity, and if you find a big diamond and you like put it in your hand, you're like, whoa, that's cold. But the trick is you have to move it out of your hand real fast. Sometimes they'll put it on people's tongues. I've never had that happen to me. I don't put diamonds on my tongue or had a diamond big enough to put on my tongue. Right? Then it feels really cold. But again, the trick is to remove it quickly because it draws the heat out really fast. But it'll equilibrate quickly. So as long as the outside temperature, so the ambient temperature, is not 37 degrees, so body temperature is 37 degrees, diamonds will feel cold. And 37 degrees, that's pretty hot, right? So most of the time, most of the weather, it's cooler than 37 degrees Celsius. So about 98, 99 Fahrenheit. So and because of that, we thought, oh, it's magic ice that's always cold. It doesn't melt. And we've even seen rings from the Roman Empire time, gold diamond rings. They don't cut the diamonds, but because diamonds has like a very, has a zinc blende structure. It looks like a octahedron. So it's very, I don't know, have you seen them in movies, like uncut diamonds, kind of like fluorite. Anyways, we can look at that later. I don't think we have time today. Okay, so back to properties. Physical change, so this capital delta, this triangle, that's the capital Greek delta. So that triangle means, that means change. So Greek, so like this is alpha, upper and lower alpha. This is upper and lower beta. This is gamma. And then this is, oh, the wrong way. That's delta. Maybe you might see some similarities to our alphabets as well, but capital delta means change. And like other symbols mean other things. So like lowercase alpha means proportion, and lowercase delta means partial. So, but that's not important really. But capital delta means change. So physical change means any change in state or appearance, and a chemical change is a change in composition. So, and whenever there is a chemical change, there is almost always a corresponding physical change. The only exception I can think of that where there is a chemical change without a physical change is that you can change the crystal structure of metals and it can change its reactivity. So iron 110 is very unreactive, at least on the surface, and iron in different, so the different forms like 111 or 211 are very reactive. And it's still, that iron is still going to have the same magnetism, density, all these things, but the surface is going to be differently reacted. It's going to be reactive in a different way. So that's the only exception I can think of that rule where you have a chemical change without a physical change. But everything else, whenever there is a chemical change, there's a corresponding physical change. So magnesium metal, it's grayish like most metals are, and it's flammable. You can light it on fire. It gets really, really bright white. Have you ever seen fireworks with big charges of white light? That's magnesium. And it turns into magnesium oxide. It's a white powder. So, or I should say white substance. It's not shiny like magnesium is. It's not bendy, so it's not ductile like magnesium is. It doesn't burn, so it's a new substance. But if you go simply, it has a different melting point. It has a much higher melting point now. So the chemical change has now different physical changes as well. So, okay. So what do you think? Digestion, is this a chemical change with a corresponding physical change or a physical change only? It's a chemical change. Break your food down, it's new substances, you can break it apart. Ice melting, chemical change or physical change only? Physical only, yeah. Iron rusting, chemical, yeah. So there's a physical change too. Iron goes from silver gray colored to brownish colored, right? So there's a physical change, but there's a chemical change too. The atoms are exchanged. Iron becomes iron oxide. Okay, and we're going to change topics yet again. Sorry, first chapter, do it a lot. Energy, and energy is, we're going to define it as the capacity to do work. The best definition is the integral of the force vector dot product with the displacement. That's a physics definition. That's the best definition. Simply put, it's the force. So a joule is the force of 1 Newton over a meter. That's more like, I guess that's about a kilogram. So yeah, that was about a joule. This takes about a joule of energy to do that. That's the work of 1 joule. So, but what is this force in ds? What if I'm moving it like this? So it's a different path. And then the integral says you sum that up all over. Okay, but intro class, we're going to do the simplest definition, and we're gonna, or one of the simpler ones, we're gonna say it's the capacity to do work. So I don't have any children, but I got nieces and nephews, and they are full of energy. You should see them. They're always, especially Christmas morning, man, they could power a city with the amount of energy that they have, right? You know, but what do they do with that energy? Do they do the dishes and clean up their rooms, do some work? No, they're kids. They're having fun, playing, right? So energy is the capacity you could do work. So different forms. Potential energy. So I can give this textbook some gravitational potential energy, and if I let it go, it turns the potential energy into kinetic energy, the energy of motion, right? And we do this with our water. We put our water up high. So for that reason, we don't need pumps. So if you ever go to see where we store waters, we store them in big containers on the hill. They usually paint them like green or brown, so they don't look very like conspicuous. So, but we put them up high in the hills. We don't nearly need water towers here. In the mainland, a lot of places have water towers, like somewhere flat like Kansas. It doesn't have any hills. But you put them up on water towers, so all you have to do is open up your water tap, and all a water tap is, it's a tube that has a kind of a cone cut up into it, and it has a like a needle head that sits in there. And when you pull the tap, you pull the needle up, and the water just rushes right through, and just uses gravity. So it's really easy to use. So we can store water that way, and store energy that way. We can also store potential energy in chemical potential energy. So like calories and food. So I can get 100-calorie chocolate bars, a real tiny one. So really tiny chocolate bars got 100 calories. That means I could burn it, and I could take 100 grams of water, raise it 1 degree Celsius. Or I could eat that and then go, jog a lap. Or I said we'd be a little more for 100 calories. I could jog 4 laps. I'm a big guy. I don't need as much work to do that. So I could turn that chemical potential energy into then kinetic energy if I wanted to. So what is heat and temperature? What type of energy is that? That's kinetic energy. So temperature. Temperature is a measure of kinetic energy on an atomic and molecular level. So more specifically, it is average translational kinetic energy. So me right now, I am moving very translationally. Up, down, forward, back, left, and right. Is there any other way I could move? How? Up. Well, that's still translation. I could twirl. Okay, I could rotate. Anything else I could do? That's this main. Cartwheel, yeah, that would be rotational. That would be rotational and translational. I could shake. I could vibrate. So water molecules. So this is, not Shaka, but so oxygen, hydrogen, water molecule. So this is translational energy. It's moving around. Okay. It also has rotational energy. So you ever wonder how a microwave oven works? Microwaves work by causing molecules to rotate. So specifically water in a microwave oven. So you take you have your pizza in the microwave oven. What happens? They start to rotate, and it's cold pizza, so it's moving slowly. But then one hits the other, and it turns the rotational energy into translational energy. And then the average translational energy, temperature goes up. So then it's rotational excitation, then by molecular collision, then it turns into translational energy, meaning temperature. Infrared light makes molecules vibrate. So if you feel heat, you go put your hands over the fire, you feel the heat, you're making the molecules in your hand or whatever you're warming up, you're making them vibrate. Then the same idea. Collision, then it turns it into temperature. So that's how you heat things up, or how you can heat things up. So, and then electromagnetic radiation, light is a form of electromagnetic radiation. So we'll talk a little bit more about that. Not so, I guess in chapter 7, we'll talk about it quite a bit. Yeah, and here is another, so fundamental forces. So we're in the physics part of it. So you can see I've listed 5 there. Physics started off by saying 4 fundamental forces, and the name kind of stuck. But then some people say 3 to 5. So different forces. Number 1, gravity. So it is the weakest of all the forces. It is ever positive. It is felt, and it's the same for both matter and antimatter. So I've mentioned what is antimatter. We won't talk about antimatter that much in this class. But antimatter is the same as matter, but has different charge and handedness of spin. So what is a spin? We'll talk about it in chapter 7, or chapter 7. It is the projection, the overall pointing of the magnetic field of a particle. Okay, and we give matter just because we choose to. We call it the right-handed rule. So meaning, if you have a wire and you run current through the wire, so if the current is moving this way, the magnetic field lines go in this direction across a wire that has a current going this way. That's the magnetic field goes this way. If I had a wire that was made of antimatter and I was running positrons through it, it would be the other way. It would be the left-handed rule, and the magnetic field would go this way with that. So that's all that means. It's just the handedness of the way that well, as I said, vector cross product. It's the manner in which the magnetic field of that particle is projected. It's one hand. We give matter the right-handed, and antimatter is the left-handed. But both experience gravity in the same way as far as we can tell. Electromagnetic chemistry, you could argue, is a study of this force. This is positive repel, negative repel, positive attract. So, and all the other things therein. So things like friction. What is friction? Friction is the electron clouds of my hands as they're rubbing up against together. They repel, and it turns this kinetic energy into temperature, into to average translational energy. Also, the fact that I have to force my hands across each other. There's the electrostatic repulsion, electromagnetic repulsion from that. So chemistry is really all about the electrons. So then nuclear weak. So nuclear weak, atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of smaller particles called quarks. What binds quarks together is nuclear weak force. It turns out these two forces are the same thing. Okay, and then nuclear strong force. So let's think of carbon has 6 protons in the nucleus. Protons are positively charged. The nucleus, these 6 protons want to fly apart. So how is it you can have 6 protons in such close proximity to each other? There's a force stronger than the repulsion that keeps it together. And then you can, after you go lead though, lead is the, maybe even, people can argue bismuth, but bismuth or lead, there's too many protons in the nucleus and they become unstable. An unstable nucleus is also known as radioactive. So, and that's really our basis right here for how we understand things. It's the nuclear strong force is because it's there because it's stronger than the repulsion of the nucleus. Kind of scary. The last one is dark energy. So you look at the Big Bang. So Big Bang happened 13.8 billion years ago, thereabouts. And you think, okay, massive expansion event. So you think, okay, well, the universe should expand like this, just kind of a constant state. Actually, the universe is expanding like this. It's accelerating as the time goes on. How does that happen? How is that possible? Say dark energy. We have no idea, right? This is just something we say. Some people add it in the list of forces. Some people only say 3. So take your pick, either one, and whatever you prefer. So how are we doing so far? Questions? Oh, and I guess I also I didn't mention this. I mentioned string theory. I said that string theory isn't real yet. String theory has not been proven experimentally. So string theory is proven mathematically. So it's a theory that is proven mathematically, but it's not considered a scientific theory yet because it hasn't predicted something that we can prove. So we're looking for that. So when that happens, then string theory will be considered a valid scientific theory. Right now, it is not. The other thing with string theory is that there's many different types. There's not just one theory, and who to say which one's right. So with string theory, it breaks everything down into strings of energy that vibrate in various frequencies in the strings, and then you can build that up. And what's nice about string theory is that you can take things like protons, neutrons, and electrons and come up with like the orbit of Mercury. You can't do that with quantum mechanics. You can't start with quantum mechanics and then have general relativity. So there's a disconnect there. And we're trying to connect all the branches of physics together into one grand unified theory. So string theory has potential to do that, but there's many different types of string theories, and it might just be some crazy math model and have nothing to do with reality. So we're looking to find some way to probe it so that we can actually verify string theory. And when that happens, quantum mechanics will be out, string theory will be in. But until then, we'll still have the quantum mechanical model of the atom. Okay, units of measurements. If we were in a not American nation, or I should say, I guess there's only one American nation. Well, United States of America, so there's Canada and Mexico and Latin America there. But non-USA nation, maybe a little bit England. They do this in England too. They do miles and inches, although they say they don't, but if you go there, they really do. But everywhere else in the world uses the metric system, and we don't. But science uses the metric system. And we have some base units. So length, meter, mass, kilogram, time, second, temperature, Kelvin or Celsius, amount, mole, current, ampere, luminous intensity, candela. No one uses candela anymore. We usually use energy to describe light. So watts or joules. A watt is just a joule per second. So meter, and the definition of these also change. Meter used to be a certain distance between the equator and the North Pole divided by a certain amount. I forget which one it was, but they needed a more accurate. Now the meter for us is how long it takes light to travel a certain distance. So our time and length are intertwined as far as definitions. Mass is a kilogram. It used to be water at 4 degrees Celsius. So water is very dense at 4 degrees Celsius, and one cubic decimeter, so a meter, and 1/10 of a meter, a cube of that's also known as a liter. A liter of water at 4 degrees Celsius has a mass of 1 kilogram. So now, though, what we use for mass a kilogram are blocks of platinum, and we have a couple different blocks of platinum. And the problem with that is, number one, they're not the same mass. Number two, they're getting lighter. They're evaporating. So what might happen in the future, they're talking about doing this. The mole is also based off of carbon-12. We might change the mole to a sphere of silicon, and a silicon of a certain distance, or diameter. And the kilogram and the mole may become tied to the same standard. So that might happen in the future, in the relatively near future, actually. Next, maybe even as short as 5 or 10 years. But either way, we have base units, and we can derive other ones, like a Newton, the force Newton. It's a kilogram times a meter divided by seconds squared. And all these things. So like a joule is a Newton meter, Newton times a meter. A watt is a joule divided by second. So a watt, so if you have a 100-watt stereo, means you have 100 kilogram times meter squared over second cube stereo. So mass times distance squared over time cubed. Okay, and other thing about the metric system is we take base units and we multiply them by something. And you can use the same unit to describe many different things. So starting at 0, you can go up, not on here, but deca means 10, hepta means 100, and then kilo is 1,000. So I used to live in Budapest, Hungary. You could order things in decagrams. So instead of a quarter pounds, they have decagrams there. So in hecta, like maybe you've heard of a hectare. A hectare is 100 square meters. So then going up, you probably mega, giga, tera, penta. You release up to tera, you know that from computers, right? Although it's not a kilobyte's not 1,000 bytes, it's 1,024. And a byte's actually 8 bits, but close enough to 1,000 that we call it a kilo. You can go down to milli, micro, nano, pico, femto, atto. But one thing, like with not like the American system or what we call the imperial, what everyone else calls the American system, like inch, like a micron is 1,000th of an inch for small things. We have an inch, we have a foot, we have a mile. So 12 inches in a foot, 5,200 feet in a mile, really not very easily interchangeable. So whereas kilogram, so my mass, I'm about 118 kilograms. An electron is 9.11 times 10 to the minus 31 kilograms. The sun's mass is about 2 times 10 to the 30th kilograms. So using the same unit, I can describe, many different things. So mass of stars, planets, and something tiny like an electron. So, and everything in between. I can use it to describe a car, a human, a basketball, a watermelon, and an insect's wings. So just and doing it all by factors of 10, which makes the math real easy. Okay. And so other things, so extensive property. Extensive property depends on the amount. Intensive property does not depend on the amount. So density is intensive, does not depend on the amount. Does it matter if I have a drop of water, if I have this much water, or an ocean of water, assuming it's all water, not a mixture? Same thing, same mixture. Does the density of any of those things change? No, they're all the same. So the density of water doesn't matter if it's a drop, if it's a glass, or if it's an ocean. The density of water is about, at a certain temperature, it's about 1 gram per cubic centimeter. Density does not change. Oh, which is the other point about liquids, they tend to be incompressible. So they actually, you can compress them a little bit, but they're incompressible. Like your brake lines, like when you put your foot on the brake, and the brakes work when your car is off even. The reason for that is the fact that liquids are incompressible. Their density does not change. So meaning you put your foot on the brake, and what happens is that the force of the brake carries along a line to the road, to the caliper. Your tires on a rotor, so you have the axle and you have a rotor, and your tires are on the end of your brake caliper. You have 2 pieces of ceramic that when you press on the brake, they go around, they snap onto the rotor, and then the friction is what causes it to stop. So, but pushing on the brake, you cause that to snap, the caliper to press on the rotor of the wheel. And so if you get air in your brake lines, does that ever happen to you? You push, nothing happens. It's also really easy to push when you have air in your brake line. So the liquid, though, is incompressible, and that's because the density doesn't change. So you can use it for hydraulics to move things, to carry forces. Okay, so that's intensive property. Extensive property does depend there. We have seen them as kids. As a kid. That was back when I lived on the mainland. Okay, so we're done with Chapter 1. Chapter 1 and Chapter 2 go by pretty quickly. Oh, and class is over. Anybody have any questions? Okay, well, I will see you next class then. Good old Wednesday.